The indirect method of proof is equivalent to what is known as proof of contradiction. Then the lines of argument if P then Q are as follows. Then how hypothesis assume that PQ is false. Because since we need to prove this as true, we have to assume that it is false. Assume that P is true and Q is false. Then the analysis part will be starting with the hypothesis that Q is false and employing the rules of logic, other known facts, infer that P is false. This contradicts the assumption that P is true. So, conclusion, because of the contradiction arrived in the analysis, we infer that P is, if P then Q is true. Provide a proof that the contradiction of the following statement for every integer n. If n square is odd, then n is odd. If n square is odd, then n is odd. So contradiction of this is if P then Q must be false. The given statement is P to Q, where P is n square is odd, Q n is odd. Then hypothesis assume that if P then Q is false. So it is P is true and Q is false. Then if P is true, that is n square is odd. And Q is n is odd. Then n will be taken as 2k because n is not odd. Q is false means n is not odd, so n is even. N equals to 2k. Then we will consider n square. N square equals to 2k whole square, which is even. This implies that P is false. This contradicts the assumption that P is true. So we will consider if P then Q is true. The square of an even integer is an even integer. Proved by method of contradiction. The statement is of the form if P then Q. P is n is an even integer. N square is an even integer. Assume that if P then Q is false, then P is true, Q is false. So n square is not an even integer. We will consider that as n square n into n is not divisible by 2. So n is not divisible by 2. N is not divisible by 2 even integer means n is not an even integer. So P is false, which is a contradiction. So conclusion, the given proposition if P then Q is true. Prove that if m is an even integer, then m plus 7 is an odd integer. M is an even integer. M is even. M plus 7 is odd. Assume that if P then Q is false. So P is true, Q is false. M plus 7 is odd. Let us consider m plus 7 is odd. Then they are given m is 2k. Is m plus 7 is odd, but we have to consider it as not odd. Then it is even. So m plus 7 is 2k. M equals to 2k minus 7. 2k minus 7 will give you 2 minus 1 plus 1. At the end of this m, you will get 2k minus 8 plus 1. 2 into k minus 4 plus 1, which is an odd. So P is false, which is contradicts the assumption that P is true. Conclusion, the given proposition if P then Q is true. Prove that for all real numbers x and y, if x plus y greater than or equals to 100, then x is greater than or equals to 50, y is greater than or equals to 50. Consider two real numbers of x and y. Given statement P, if P then Q are R, if P then Q are R, then we have to consider P is true and Q are R is false. Then Q is false and R is false. That is x is less than 50 and y is less than 50, assuming that. Then x plus y is less than 100. P is false, which contradicts the decision which we taken. This is given statement P if P then Q is true. Prove that there is no rational numbers whose square is 2. Let Q be the set of all rational numbers. The given statement for all x belongs to Q if P then Q. X is a rational number, x square not equal to 2. There is no rational number whose square is 2. Then their proposition is if x is a rational number, then Q means x square is not 2. We will consider if P then Q assuming P is true and Q is false. Let us consider x square is 2. So x square is equals to a by b, where b not equal to 0, where a and b are some no common factors. We know that x square is 2. So a square by b square equals to 2. A square equals to 2 into b square. A is even. So a is 2n for every n belongs to z. Then 2b square equals to a square. So hence b is also even. So a and b are even, which has 2 as a common factor, which is a contradiction. So for every x belongs to Q, if P then Q must be true. Give a direct proof, indirect proof, and the proof of contradiction for the following statement. If n is an odd integer, then n plus 9 is an even integer. Let us consider if n is an odd integer for direct proof. N equals to 2k plus 1 for every k belongs to z integers. N plus 9, 2k plus 1 plus 9, 2k plus 10, that is 2 into k plus 5, which is divisible by 2. So n plus 9 is even, hence the proof. Indirect proof hypothesis, assuming that n plus 9, if p then q, p is n is an odd integer, then n plus 9 is an even integer. If p then q for contrapositive, we have to consider n plus 9 is not an even integer, that is a contrapositive. N plus 9 equals to 2k plus 1 odd integer for every k belongs to integers. Then n equals to 2k plus 1 minus 9, which will give you 2k minus 8. Then 2 into k minus 4, which is divisible by 2. N is even. Conclusion. This proves that contrapositive of this given statement is true, hence the proof. Proof of contradiction. Contradiction, if P then Q, then contradiction of this will be P is true but Q is not true. Q, what is Q? N plus 9 is not an even integer. So that we will consider n is odd and n plus 9 is odd. N plus 9 equals to 2k plus 1 for every k belongs to integers, then n equals to 2 into k minus 4, which is even. This contradicts the assumption that n is odd, hence the proof.